Hello, everyone. My name is Frédéric Desbiens, and I'm Program Manager for IoT and Edge Computing at the Eclipse Foundation. Welcome to this session where I will try to explain what edge computing can learn from the moon landings. Before I get into the specifics of the moon landings and everything around them, I think it's important to define a bit what I'll be talking about, especially if you are younger, maybe you didn't witness those things live. I know that I was a few years late myself. But essentially, I will refer a lot to those terms throughout the presentation. So on the left, you see what is called the command module. And the command module is the little capsule at the top. It's literally the only part of the Apollo spacecraft that came back to Earth. And this is where the astronauts were most of the time, right? And below it, so the largest part of the spacecraft on the left is what is called the service module. And the service module is essentially a place where they had the tanks for fuel and oxygen and stuff like that, and lots of instruments, obviously. You see antennas, for example, at the bottom, that were used to track the spacecraft and that kind of stuff. So anyway, that's one component of the hardware. And then the other part, the lunar module. The lunar module is what the astronauts use to descend on the moon, as you can see. And it was in two parts as well. So the base, the golden part that you see at the bottom, wasn't meant to return or to lift off. So essentially, when the astronauts were down with the moon, they were just lifting off with the top part of it. And that's about it. So when the rocket was lifting off, all of those two things were stuck together in the rocket, and they were flying together to the moon. Then lunar module was separating, going to the moon. Only the top was getting back to the common module. Then the astronauts, just ditched the leftover part of the lunar module and came back to Earth. All right. One striking thing now about the Apollo missions is that they happened a long time ago when you consider it. I mean, and in 2019, in fact, we celebrated the 50th anniversary of the first moon landing in 1969 with Apollo 11. But when you look at the IT infrastructure behind it, it's striking how much it was edge computing before the time. And here is a very simplified view of the IT architecture for most of the moon missions. Okay, so details could change from one mission to another, that kind of stuff. But essentially, the principle is that you needed at least 3 big antennas on Earth in order to track the spacecraft. And when I say track, it's all of the telemetry from the sensors that were on board, but also all of the voice chat and that kind of stuff. And those 3 antennas were one in the US, one in Spain, one in Australia, obviously, to take into account the rotation of the Earth. And below or on site with each of those antennas, they had UNIVAC mainframes, okay, that were collecting the data, and the data stream from the spacecrafts, and this covers both the common module, the service module, and the lunar module, so all 3, okay, those were 48 kilobit per second links, from the spacecrafts to the antennas. And the mainframes there were churning some of the data. And then they were sending that to the mainframe that the consoles in the command room. So you see a photograph of the command room in Houston on the left of the slide. And all of those consoles, they have screens, and they were showing screens from mainframe programs that were running. But the mainframe had the capacity to process roughly 2 kilobytes per second worth of data. So this is why you needed those UNIVAC mainframes close to the antennas to mash all of this data up in a form that the mainframe could consume and then show in real time to the crews in Houston. So even though, we're talking about an era of computing that was much more primitive than today. And even the mainframe that they were using to display the stuff to the controllers was not a top of the line machine for the time or anything like that. It was a mid-range machine, still cost, a healthy dose of millions, but still, It wasn't even top of the line for the time. And you see that they were doing edge computing before the time, before we were talking about IoT or anything like that. And in fact, space travel is probably one of the prime examples of what you do with, the Internet of Things, in the sense that you have connected objects, in this case, the spacecrafts, or even the astronaut suits themselves were full of sensors, and you're sending that data back. And obviously, in the case of the spacecrafts, this is also a command and control scenario. And just to illustrate how much sensors there were, I put a little diagram in the bottom right of the slide where you see essentially, the instrument cluster that was in the Saturn V rockets. Okay, so the lunar module and command module were sitting at the top of that, but you had lots of sensors and other equipment in the rocket itself. And, this was a whole section of one of the stages in the rocket that was full of equipment, as you can see in this little diagram at the right. So, edge computing before the time, IoT before the time, really the Apollo missions were a triumph of human ingenuity. And we can learn from that. We can learn from that even today, even with all of the progress we've made in IT. The first lesson really stems from the basic design of what is called the Apollo guidance computer. Okay, and you see what that computer looked like from the outside, at least on the background of this slide. So the big golden box is the body of the computer itself. It weighed about 80 pounds, so that would be, well, what, 50 to 60 kilograms, I guess. And on the right, you see the only UI that the astronauts had in order to operate and monitor the computer, which is called the disk key. And the disk key was operating on a very simple paradigm where essentially you typed a numerical code for a verb, so an action that you wanted to do. You typed a numerical code for the noun, you pressed enter, and then the computer was either running a program or returning you data from the various sensors on board. And I mean, already there are tremendous lessons for edge computing just in the design of this computer. For example, well, in terms of compute power, it's literally an incredible example of constrained computing. I mean, your microwave in your kitchen right now probably has more compute power than the Apollo guidance computer. And you found one of those computers in the command module and one in the lunar module, and they were literally the same machine. It's just that some of the programs differed because obviously, for example, the common module didn't have to land on the moon, so it didn't have that part of the code and that kind of stuff. Anyway, so the literal design of that computer is really a lesson. For example, it had only the equivalent of 4 kilobytes of memory. Okay, and that wasn't a lot. That really wasn't a lot, but that memory could keep the values in memory even between reboots. So the computer didn't have separate storage. The main memory was all that it had, but all of the values could stay even if the computer was rebooting. And that's an important thing because essentially it made the computer highly adapted to the kind of scenarios that could happen. The programs that were running on that computer were controlling, the firing of the thrusters. They were controlling many other parameters and important telemetry that without them, the astronauts would have been in danger of losing their lives, literally. So in its design, the computer incorporated the idea that even if it was rebooting, all of the tasks that were in memory at the time of the reboot would resume exactly at the same point in the code when the computer would be restarting. And this literally, as we will see a bit later in the presentation, this literally saved the lives of the astronauts because essentially the computer rebooted quite a few times during the flights, as you will discover. So all in all, you look at the design of this machine, which is very primitive in some ways by today's standards, but you can see that designing according to the specific requirements is especially important. And in this case, the custom design that they used was incredibly useful in the missions. So the lesson number one that we can learn from the Apollo guidance computer is really architecture for reliability, okay? Especially when you consider most of the use cases for IoT and edge computing. Yeah, if you're just gathering in a digital building some temperature and humidity data, okay, maybe this is not mission critical. But if you're operating a petrochemical plant, if you are operating a tank on the battlefield or whatever, a drone, you know, all of those things have very, very strict requirements, and most of the time will require real-time OS. So from the ground up, you have absolutely to take that into account, even if you're doing edge computing. And it's important in the case of edge computing that you assume that the networks, you know, will be unreliable. Okay, that's really important. So using REST, you know, just doing web service calls the old-fashioned way won't cut it there, because the network won't be reliable, the bandwidth will vary, at sometimes the network won't be there, and you have to take that into account in your architecture and into the basic decisions that you will put into your code, and that's really essential. Then be stateless whenever possible. So I told you that the computer was able to reboot and then restart execution exactly at the same point that the tasks were at the time of the reboot. And it's really fundamental, you know. So this computer was essentially stateless, and you know, read from memory or read from its permanent storage, whatever state it had to be in at the moment it rebooted. And this made the overall solution much more robust. And the third lesson here is to virtualize and containerize. Really, VMs and containers are incredible tools, and we take them for granted. But when you look under the cover a bit at the design of the Apollo guidance computer, really what you realize is that they were doing VMs even before the time. But can you imagine that, doing VM in using a processor that's roughly equivalent to what you had in the 70s in an Apple II, and with 4 kilobytes of memory? I mean, you know, the people that wrote that code were incredibly good. And in fact, throughout the Apollo missions, you know, there was never a single bug that was found, you know, at runtime during the missions that could have affected the lives of the astronauts. And all of those efforts around the Apollo software, by the way, they were led by a woman, Margaret Hamilton. And so go woman in IT, we need more of you. All right. Now, let's talk about two specific incidents that happened during specific Apollo missions to illustrate or find other lessons that edge computing can learn about. And the first one is during Apollo 11, error 1202. Well, there was error 1201 and 1202, they go together. But essentially, what happened? Imagine you are Neil Armstrong and Buzz Aldrin. You are in this little lunar module. Here we see the Apollo 11, the top part, you know, coming back to the common module after the moon landing, okay? But imagine you are strapped into this and you are about to do what no human did before, which is literally land on the moon. There are so many unknowns, you are incredibly stressed, and you must to be calm and composed in order to do everything that you have to do, right? So many things are happening at the same time. And then the computer starts to tell you error 1202 all the time. And you have no idea what this is about. And so obviously at the time, you know, they didn't have the space or the screen estate or anything like that to display more meaningful error messages. So the astronauts had to memorize lots of those codes and their meanings, right? But in this case, it was a little, you know, a little used error code that meant nothing to them. So imagine you are, you know, descending to the moon, you will land in a few minutes, and you have to make a decision about this error. What should you do? Because, well, it could compromise your life. So maybe you have to abort the mission and get back to the common module. Well, fortunately, there was one member on the ground team back in Houston that essentially had made little cheat sheets of all the codes. And when the astronauts asked ground control what this error was about, the guy was really was easily able to find out. It was that the onboard computer of the lunar module was lacking temp space. In other words, it didn't have, enough memory in order to allocate new variables for the programs that were in memory. And at the time, they weren't sure. They weren't sure exactly what was causing that or anything like that, and they had to make a call. Okay, do we abort the mission or do we let them continue? And well, the end. They continued. The ground control told them that it wasn't a big deal, that the computer would reboot, okay, and that they should ignore the error codes. So throughout the descent to the moon surface, Armstrong and Aldrin, all those errors coming up from time to time, and the computer was rebooting and rebooting, but still continuing to execute all of the critical programming it was supposed to perform for a successful moon landing. And they landed. Okay, after the fact, they understood whatever was happening. So I'm simplifying a bit there. So if you are really, really knowledgeable about this, you will tell me my explanation is a bit simplistic. But essentially, there was an onboard radar that was defective and flooding the computer with unneeded data. Okay, that data was taking all of the temp space in memory, and so this prevented the programs that were important from allocating memory to new variables. Okay, and that's what happened. And they were right to ignore those errors, in the sense that the design of the computer made it secure for them to continue the descent. But still, it's an incredibly stressful situation to be in, especially when you're just casually trying out to do something no other human did. Okay, so what can we learn from that? Well, essentially, I think the lesson there lies in the fact that you should pick the correct sampling rate for your use case. Okay, so in this case, the sampling rate was excessive because of a defective piece of equipment, but please don't oversample. And if you're stuck with sensors that return too much data by design, then process only the data that you actually need. If you are designing, I don't know, a solution to monitor a digital building, you don't need to return the current temperature and humidity 1,000 times per second. Maybe returning every minute is sufficient. On the other hand, if you are working on something that we control, an oil and gas refinery, or I don't know, a tank on the battlefield, or something that's really time sensitive and mission critical, then maybe you need more data. But once again, you have to figure out what the right sampling rate is according to the functional requirements that you've got. And that's really an important job that you should do even before writing a single line of code or starting to solder, the first batch of components. And the other thing is that you have to take into account that sensors can go haywire. And that's really important, because you saw that error being made again and again and again. The recent problems with the Boeing 737 are a good example of that. I mean, it's an incredibly sophisticated plane, but it had only a single sensor to measure the angle of attack. Okay, and that led to the two catastrophes that happened with two of those planes. Since the sensor was defective, it was returning erroneous data to the computer, and the computer was running software that wasn't appropriate for the current situation of the plane. So if they had at least redundant sensors and some validation logic, they could have maybe not completely avoided the problems, but at least it would have been much easier for the crews to mitigate them, because one of their data sources about the angle of attack would have been still returning correct data. Okay, so once again, you have to expect that something will go wrong about the network, about your sensors, about everything, and we don't do this enough already in the data center, but doing it in the case of edge computing in IoT is incredibly important. Okay, let's now focus on another Apollo mission, Apollo 13, and the story of its air filters. So what you see here is a photograph of the Apollo command and service module for Apollo 13. And you see there's been an explosion. There's a whole side of the service module that obviously has exploded. So there's a movie of the same title, and I'm sorry to spoil it to you if you didn't see it or are not aware of the mission. So turn sound now off if you don't want to hear about this. But essentially what happened is that as they were assembling the service module on the ground, there were those big tanks for oxygen and fuel, and they dropped an oxygen tank on the ground just by a few inches. You know, it was just a little drop like that, and they inspected the tank and it looked fine, and they put it, you know, on the spacecraft anyway. But this fragilized some of the electrical wiring inside the tank, and that electrical wiring was important because throughout the flight you had to heat and you know, churn a bit the contents of the tank to ensure that everything was at the right temperature and that the thrusters could be fired when needed. And so at some point where they tried to start the heating, because the electrical cable was frayed because of the drop that the tank had a few months before as the spacecraft was assembled. Okay, this started a fire, big explosion, and now the whole mission is in jeopardy. So they were en route to the moon, and they had to figure out a way to survive. And essentially the way they handled this is that they use the lunar module as a kind of live, you know, emergency life craft, and the whole crew, you know, powered down the command module. They all stayed in the lunar module for a while as they circumvented the moon and came back to Earth, and then they reactivated the command module as they were getting close to get back into the atmosphere, because that was literally the only part of the spacecraft that could survive that. And in the end, they survived, but certainly, you know, it was a close call. And one of the problems that they ran into is essentially that one of the problems they ran into is that the air filters in the command module and the lunar module didn't have the same shape. Okay, and it's really important because they couldn't reuse them, and so they had to figure out a solution on the ground. You know, so they put a bunch of engineers in a room with you know, all of the equipment that they had in both the command module and lunar module, and told them, you must literally find a way to have those square filters fit the round filter space in the lunar module. Okay, so the design was that the air filters in the command module were square. In the lunar module they were round, and so they had to find a way to make those square air filters fit in the lunar module, where they would stay 3 of them instead of 2, and for a much extended period of time as they were circumventing to the moon. And this was critical to keep the crew alive. So what's the lesson there? Well, essentially, standardization pays. Stick to vendor-neutral platforms. You know, if you're using a little special flavor Kubernetes that only your vendor has, you are painting yourself in a corner. And another dimension to be aware of is that the best edge platforms are really aware of the capabilities of the hardware. So you see on the photograph, you know, the kind of MacGyver type of solution that it came in order to have the filters fit in the lunar module. And in the same way, whatever edge platform that you leverage must be aware of the capabilities of the hardware that's available on the nodes. That's really something important. Anyway, so that was lesson number 3. Now, all of those lessons and many other come from the work that we are doing right now in the Edge Native Working Group at the Eclipse Foundation. And the goal of the working group, we are code first because we're not focused on proof of concept code. We're not focused on blueprints or architectures. We are focused on 2 real-world platforms that you can leverage now in order to streamline and simplify edge mass deployments and implement what we call edge native DevOps. So that's DevOps and the cloud native principles adapted to the context of edge computing, because it's very different from cloud computing and cloud native. You see here the founding members. So we are a diverse bunch and obviously always looking for more. So if you are interested in that, please reach out to me. And what we've got are two production quality commercial grade platforms, Eclipse IO Fog and Eclipse Fog OS. It's written Fog 05, but it's pronounced Fog OS. So have a look. They each have their website and obviously more than happy to point you to information about them. And what we're trying to do in Edge Native is really to build an Edge and IoT ecosystem in, interacting with all of the great tech that's already existing. So whether it's Kubernetes, KubeEdge, K3S, EdgeX Foundry, whatever. But when you look specifically at what we have at the Eclipse Foundation, or in the case of Project Scopper from Red Hat, it's not at Eclipse, but it's a project that we collaborate very, very closely with. You see how much breadth and depth we have in our tool lineup. So if you are interested in the Eclipse Edge Native Working Group, please have a look at our website, edgenative.eclipse.org, and follow us on Twitter as EdgeNativeWG. And now I guess would be the time for questions. So let me stop sharing here and have a look at the questions. All right. Okay, so a question here. The Air Force has tested Kubernetes on the plane. Do you think we will see Kubernetes running on spaceships anytime soon? And do you think it is a good idea? Well, to be honest, in the current state of Kubernetes, I would say no. And the reason for this is really, really simple. A spacecraft, whether it's the lunar module or the upcoming SpaceX spaceship that eventually they will maybe use to go to the moon, all of that, as strict real-time requirements. And to my knowledge, this is not something that's really taken into account in Kubernetes specifically at this point in time. There are many, many points of failure in any Kubernetes deployment. And I think it's it would be too tricky and the stack too complex to be reliable in the kind of life-threatening scenarios that we see. However, VMs, containers, and principles like that are important, and things should be leveraged. And maybe at some point we will have real-time Kubernetes, but there are those disclaimers that say on the Java virtual machine, on our Kubernetes, this code shouldn't be used to run a nuclear plant or whatever. So if you cannot run a nuclear plant with it in real time, you shouldn't put it in a spacecraft as well. And now a second question, how do you see the mission critical requirements are addressed in modern edge computing, e.g. for use in factories, not critical as moon landings maybe, but still more than just reading some sensors. So the way to address that, you need a multi-layered approach, I think. One component of the solution is obviously to use real-time operating systems. Okay, the fact that you will have predictable latency in your execution and that you have the guarantee that if you launch an order to a specific piece of equipment, it will be executed in a specific amount of time. Okay, and that's really important. Then you have to think about the network. There's a concept emerging in a networking space that's called deterministic networking. And that's really important in the sense that you have predictable latency, not only in a compute perspective, but in a transmission perspective across a local network. And that's really important because by default, on a Ethernet network, you have to remember that there are collisions at the time. And the solution for that is not that the Ethernet protocol will not avoid the collisions. It will just keep resending. Now you can have quality of service and stuff like that to improve the thing a bit, but this is not enough to produce a specific and predictable amount of latency between nodes on a local network. So taking that into account is really, really, really critical. And then there are many other components, obviously, to the solution. But I think that using a good real-time OS and deterministic networking are maybe the two most important ones. Another question was that there are other Eclipse platforms that are edge related, like Kura and Kapua. Yes, you can use Kura as a kind on your edge node, and please have a look at it, but it's not as general purpose because it's OSGI based, so you don't run VMs or containers on it. You have to write your own Java software. In any case, I'm time's up. So thank you for watching. I'm Frédéric Desbiens from the Eclipse Foundation. Please reach out on Twitter or using Swapcard if you have other questions. It was a pleasure to have you today, and have a nice rest of the conference. Thank you.